Hello everyone and welcome to the Agilent Science and Technology Virtual Symposium. My name is Kate Pearson-Santiago and I'm Associate Vice President Worldwide Marketing at Agilent. On behalf of all of the Agilent colleagues, I'd like to warmly welcome you to day 2 of our event. Yesterday, Nino Tortino, Agilent VP of Sales, spoke about the ways in which Agilent supports our customers. Today, I wanted to continue that theme and share how we are working to keep you up to date with the latest product and application solutions and support offerings. As we navigate changing conditions with the way we work, we have heard from our customers of the importance of educational content to assist and adapt to these changes. We aim to be a helping hand, albeit a virtual one at the moment for the most part. And our recent lab shutdown and restart webinar series is an example of this. As you explore the symposium today, we welcome your feedback, either via the survey or via speaking with Agilent staff in attendance. We're keen to hear from you about the topics and issues of importance to you so that we can continue to provide information and insights that support your needs. Customer and employee safety is also paramount to Agilent, and we are increasing ways to connect with you virtually as a result. This symposium is one example of the way that we are replacing many face-to-face and virtual trainings and seminars with digital, virtual, and on-demand activities. Still, like at our live events, you still have the opportunity to attend live presentations, connect via Q&A, and connect with your experts and peers. Even though it's virtual, we are still here to help and to support you. We're also looking forward to connecting with you at face-to-face events soon, and you can be assured that when we do, it will be with the utmost of safety and care. In addition to working towards a safe environment, we are also working towards sustainability, and that's an integral part of the way that we do business. Beyond designing products to enhance sustainability, we're also aiming to be sustainable in our operations. For example, when we plan live events, we work to minimise transport and logistics emissions, to go paperless, to minimise single-use plastics as much as possible, and to provide sustainable giveaways. We know that many of you and your organisations have similar goals, and we are equally committed to improving sustainability with you. And finally, staying connected is even more important in times like this, and Agilent provides many opportunities to connect via all the major social media platforms, including Twitter, LinkedIn, and Facebook. We have also recently launched regional-specific social media channels for LinkedIn and in local language in Thailand with Line. So we strongly encourage you to follow us to keep up to date with local events and topics. And so finally, again, welcome. We're very much looking forward to connecting with you today and to seeing you in the platform.
Welcome, everyone. I'm Susie Valdez, and I will be your moderator for today's event. And thank you for joining us for our presentation titled Low Energy, High Confidence, Untargeted Screening and Unknowns Identification by High Resolution GCMS. It's my pleasure now to introduce you to Paul Contreras, the Project Manager for LC Time of Flight and GC Quadrupole Time of Flight at Agilent Technologies. For a complete biography on our speaker, please visit the tab at the top of your screen. If any questions arise during the presentation, we encourage you to submit them into the Q&A box, and our speaker will address them following the presentation. Please join me now in welcoming Paul Contreras. I will now turn the presentation over to him. Welcome, Paul.
Hello everyone and welcome to today's presentation. My name is Paul Contreras, Product Manager for LC-TOF and GC Q-TOF at Agilent Technologies. Today, I'm going to talk about untargeted screening and unknowns identification by high-resolution GCMS, low energy, high confidence, Agilent GC Q-TOF. Before we discuss new developments in the Agilent GC Q-TOF portfolio, I'd like to share a brief history of how the GC Q-TOF came to be. Around 2010, Agilent recognized there was a need for a full-spectrum, high-resolution, accurate mass MSMS-capable instrument in the GC analytical space. Because of Agilent's long history in GCMS, we were well positioned to leverage many of the technologies that have been developed and refined over the preceding decades to create such an instrument. The ion source and the gold quartz quadrupole pioneered in our GCMSD portfolio, the collision cell that was leveraged from our leading GC tandem quad, and even the time-of-flight technology from our LCMS portfolio were all harmonized into a single platform in late 2011. Resulting in the 7200A GC Q-TOF, the world's first high-resolution GC Q-TOF. This platform achieved broad market acceptance across different application areas, including pesticide and other contaminant screening in food and environmental samples, metabolomics profiling, energy and chemical characterization, and more. The 7200A was followed a few years after by the 7200B, which represented a refinement to the platform with increased performance specifications and system robustness. Importantly, software features were hand in hand with this platform to help support targeted qualitative screening, compliant with SANTI guidelines, and to improve signal processing for high-resolution time-of-flight data. Both of these platforms have proven themselves analytically, especially in the food and environmental application spaces. Even so, we listened to the user community and recognized a need for an even greater analytical performance. With that feedback, we set out to create a completely new instrument to expand performance space for GCMS. This new platform was designed to provide more confident identification, more accurate quantification, and more powerful exploration capabilities. This latest platform is the Agilent 7250 GC Q-TOF. The instrument may look similar to the preceding platforms, but underneath the covers, it's a completely new instrument. One of the differences not fully visible in this image is the updated time-of-flight section. We've extended the ion flight path by 50% to increase the resolving power of the system, which also leads to greater mass accuracy. However, improvements in resolution and mass accuracy are also made possible by other technological advances in the system. One of these advances is a completely new detector electronic system. This new system can digitize MS signals at up to 10 GHz, 150% improvement over the previous generation electronics. What's more, this increased detection rate is possible across two separate gain channels, part of a significant evolution of the detector electronics. This results in the ability to acquire high resolution and wide dynamic range data simultaneously. From an application perspective, this means significant improvements in simultaneous qualitative and quantitative screening are realized. A third piece of breakthrough technology that was only found on the 7250 GC Q-TOF that promises to redefine GCMS workflows is a novel low-energy electron ionization source. This ion source, based off the high-efficiency source found in the Agilent GCMSD and GC tandem quad instruments, has been optimized for low-energy EI operation. With this technology, a spectral tilt towards a compound's molecular ion is often achievable through lowering the source ionization energy. This yields powerful analytical benefits, which we'll cover later. When designing this instrument, we wanted to ensure reliable, reproducible performance to support the user community needs as high-resolution, accurate mass systems move farther into routine use. The R&D teams who designed the instrument evaluated the components inside the mass spectrometer that have a significant impact on spectral performance and worked to define tolerances to ensure consistent performance from injection to injection and spectra to spectra. This is coupled with a completely new auto-tuning algorithm called SWARM for GC Q-TOF. It's a multi-dimensional parameter optimization routine that allows for better, more consistent tuning results achieved in a shorter time frame. Of course, the GC Q-TOF is partnered with the world's predominant GC platform, the Agilent 8890. This configuration includes a spare pneumatic switching device channel, or PSD channel, that can be used to configure capillary flow technology devices, such as backflush, which is often recommended for food and environmental matrices to reduce analytical runtime, preserve column lifetime, and reduce source maintenance. Now let's take a look at some of the performance characteristics necessary for confident compound identification in qualitative GCMS. Here we have a spectral example from our high-resolution pesticide library showing the entry for thiamethoxam. Thiamethoxam is restricted in the EU as it is a neonicotinoid that has been implicated in the decline of honeybee populations. To identify the presence of this pesticide, there are several criteria that can be followed. One of the most well-known set of criteria are the EU SANTI guidelines. These guidelines indicate that for a high-resolution full-spectrum instrument like the 7250 GC Q-TOF, at least 2 ions with a mass accuracy of better than 5 ppm must be used. With this mass accuracy requirement changing from a relative measure of 5 ppm for masses above 200 m/z to an absolute measure of better than 1 millidalton below 200 m/z. We spiked thiamethoxam at 5 part per billion, which is 50% of the maximum residue level to ensure it was detectable at below regulatory limits. The matrix we chose was avocado, since trace level detection is challenging due to the background complexity that is introduced. We then selected 2 of the characteristic ions at 182 mass charge ratio and 212 m/z. Evaluating the spectra for each of these characteristic ions at trace levels shows clear separation from nearby interferences, and excellent max accuracy of 15 millidaltons for the 182 ion and less than 1 ppm for the 212 ion, which is in compliance with the SANTI guidelines. It's important to emphasize that this identification is possible in a complex matrix at 50% of the maximum residue limit, representing a worst-case scenario for identification that we achieved successfully here with the 7250 GC Q-TOF. Mass accuracy has benefits in compound identification, and it has additional benefits, one of which is replicate precision. To evaluate this performance aspect, we performed a real-world application of looking for trace-level contaminant in a commodity. To achieve this, we spiked 1,2-dibromobenzene into 1% juniper berry oil. Using 1% juniper berry oil as the example matrix is a challenging analysis due to large background levels found in essential oils. This background level becomes apparent when evaluating the total ion chromatogram, which is shown in the center of the slide. We can see that the baseline is quite elevated with no readily available GC peaks rising above the baseline. To evaluate the spiked contaminant, we extracted characteristic ions at about 155 m/z and about 234 m/z, as shown in the library structure on the upper right-hand corner of the slide. Performing extractions of these characteristic ions show the ion at about 155 m/z is able to be extracted cleanly, as is the ion at about 234 m/z. When performing replicate injections, we are able to achieve single-digit % RSD levels. With a value below 7%, this is significant because it proves we can reliably detect a trace analyte not just once, but consistently across multiple injections. Also notable is the relative difference in intensity between the total ion chromatogram and each of these extracted ion chromatograms, which indicates the relative trace level detection that can be performed on the 7250 GC Q-TOF. While mass accuracy is indeed important for improving identification confidence and replicate precision, it isn't everything. This slide that you see here is an excerpt from a journal publication from the Fiend Lab at University of California, Davis that discusses one of the 7 golden rules of mass spectrometry. The rule being discussed here is the importance of isotopic fidelity. The rule states that a mass spectrometer with very good mass accuracy of less than 3 ppm, but also with proper isotopic fidelity, will outperform a theoretical mass spectrometer with near perfect mass accuracy of less than 0.1 ppm. When we say outperform, we mean limit the number of candidate molecular formulae for a given accurate mass measurement and restricted element list. As important and as useful as mass accuracy is, there are diminishing returns to its impact. To illustrate how important isotopic fidelity is to contributing identification confidence, we wanted to ensure the 7250 GC Q-TOF retained the excellent isotopic fidelity found on Agilent MS systems. To illustrate this performance, we have the example of dodecane, which might not be analytically very interesting by itself, but is often used to calibrate retention indices for GCMS applications. If we zoom on the molecular ion cluster at mass 170, we can see that the monoisotopic peak of the +1 isotope and the +2 isotope nearly perfectly align with the theoretical isotopic distribution. This gives us an orthogonal degree of confidence in compound identification beyond the accurate mass measurement for the molecular ion cluster and beyond a GCMS spectral library search. Another performance attribute to consider is the relative trace level of the molecular ion clusters as compared to the overall spectral intensity. The monoisotopic peak for the molecular ion cluster is about 2 orders of magnitude less abundant than the base ion on the spectra at 57 m/Z, and the +2 isotopic cluster is another 2 orders of magnitude less than the molecular ion peak. Despite the trace level of the +1 and +2 isotopic peaks, we see excellent isotopic fidelity is maintained in this example. Since isotopic fidelity is so important, we've built tools into MassHunter data analysis that allows us to easily visualize this performance aspect. A simple tool in MassHunter qualitative analysis allows for the predicted isotopic distribution of a putative chemical formula to be overlaid against a measured spectrum, allowing the analyst to get a quick visual comparison between the two for additional confidence. The data shown in this example is a halogenated phenol acquired at 50 Hz spectral acquisition rate. Even at very fast acquisition speeds, compatible with comprehensive GC by GC, the 7250 GC Q-TOF is able to maintain excellent mass accuracy and isotopic fidelity. Even with high resolution, accurate mass measurements, and isotopic fidelity, the primary tool for identification by GCMS is still by library search. This is due to the availability of hundreds of thousands of reference spectra in NIST and other commercial libraries, most of which were generated by HP Agilent 5790 series scanning Quadrupole MS systems. We wanted to ensure that the 7250 GC Q-TOF exhibited the same spectral quality as these legacy Quadrupole systems to ensure maximum utility from the vast multitudes of library spectra available. The mirror plot on the slide shows the pesticide dichlorobos with the 7250 GC Q-TOF acquired spectra on the top and the NIST library spectra on the bottom. Visually, we can see good alignment between the two spectra. Evaluating the library match score, we see that a value of greater than 93 is achieved for this organophosphate pesticide. Not only can we make use of legacy nominal mass libraries, but high-resolution accurate mass libraries can also be used for even greater confidence in spectral matching. An extensible, high-resolution library of more than 850 pesticides is available for the 7250 GC Q-TOF. Another important performance characteristic to consider is the instrument's in-spectrum dynamic range, which is a measure of the limits of concentration differences between co-eluting compounds. The example on the slide is from a metabolomics experiment, but we have environmental data on the same topic we'll share on the next slide. To evaluate the in-spectrum dynamic range of the platform, we will look at a single spectra and compare the absolute abundance of the most abundant mass peak with good mass accuracy to the least abundant mass peak with good mass accuracy. For this experiment, a metabolite was detected in a mouse lung extract. The most abundant mass peak at 73 m/Z from the derivating agent was detected at about 4 million counts with good mass accuracy of less than 3 ppm. Zooming in on the 414 m/Z ion cluster, we can go out to the +5 isotope and see that the 419 m/Z ion was detected at about 240 counts with a good mass accuracy of less than 3 ppm. Another example of in-spectrum dynamic range involving an environmental application is shown here. A combustion experiment was performed to see the relative change in the amount of PAH and other compounds before versus after exposure to a fire event. This is a screen capture of MassHunter unknowns analysis software, which shows a chromatogram pane in the upper right, a spectral mirror plot in the lower right, and component extracted ion chromatogram overlays in the center. We can see that the total ion chromatogram, as outlined in the black trace in the chromatogram pane, is quite complex with high abundance levels. The extracted ion chromatogram for our detected component, as indicated by the blue arrow, is dwarfed by the abundance of the total ion chromatogram at the solution time point. Despite this vast difference in analyte versus background concentration, we can see from the mirror plot that the 7250 GC Q-TOF spectra on the top of the mirror plot is visually extremely similar to the NIST library spectra for the putative identification of dibromophenyl ether. If we evaluate the library match score, we can see that it is of value greater than 95, despite the relative trace level of the analyte. This spectral match is possible to high resolution, accurate mass detection with a wide in-spectrum dynamic range, but it's also optimized through new developments in signal processing, which we will discuss next. Those of you who are familiar with qualitative GCMS are likely familiar with spectral deconvolution. In deconvolution, a measured spectra is evaluated for ions that are present at significant intensities. These ions are then extracted to create extracted ion chromatograms. Extracted ion chromatograms are compared for chromatographic peak shape and retention time, and those extracted ion chromatograms with nearly identical peak shapes and retention times are grouped together as a component. The ions associated with these components are assembled into component spectrum, and the component spectrum is searched against a library for compound identification. This technique works extremely well for scanning quadrupole mass spectrometers, as that is the analytical platform that the technique was designed for. While it can also be used for GC Q-TOF data, it doesn't make use of the information-rich, high-resolution, accurate mass data generated by GC Q-TOF. This is why Agilent has invented HRMS, a new signal processing technique designed specifically for GC Q-TOF to optimize analytical results. Rather than evaluate data as a set of static extracted ion chromatograms, HRMS considers the data as a continuous three-dimensional array of retention time, mass, and abundance. When visualized in this manner, it becomes clear there are persistent ridges and features which correspond to extracted ion chromatograms. However, HRMS processing is able to extract along the apex of the ridgeline rather than a static M/Z extraction. This better characterizes the high-resolution accurate mass data that's collected on the GC Q-TOF. This has a number of benefits. More sensitive detection, as HRMS is able to extract to lower levels than conventional deconvolution. More accurate mass assignments, as mass accuracy is preserved with this technique. More accurate abundance measurements with accurate signal extractions, and more reproducible compound detection with the processing we are able to achieve with high-resolution accurate mass. HRMS also has additional benefits for quantitative measurement, which we'll cover next. So let's briefly talk about targeted quantification with untargeted acquisition, a powerful combination with the performance attributes of the 7250 GC Q-TOF. To evaluate quantitative linear dynamic range of this instrument, we spiked the pesticide phonophos into avocado matrix. Avocado is a challenging matrix due to the high amount of lipids and other heavy background. Spiking levels for phonophos started at 0.5 part per billion, which is 20 times lower than typical maximum residue limit permitted by regulatory agencies, and is continued all the way up to 1000 ppb in triplicate. When evaluating the linearity, we see over 3 nines in the R-square valued in this concentration range. Zooming on the low end of the calibration curve, we can see that between 0.5 ppb and 50 ppb, the curve is still extremely linear, with no drop-off in the low end. This example shows 3.5 orders of magnitude of linear dynamic range in complex matrix while maintaining excellent linearity and consistent response factors. It's important to keep in mind that we're looking at data from a full spectrum, high resolution mass spectrometer in this example. On a targeted platform like triple quad, each of these calibration points may represent just a single MRM transition. This provides no additional qualitative information. For the GC Q-TOF, each of these data points is a full spectrum acquisition, meaning we can not only measure levels against target compounds, as is shown here, we can perform multiple simultaneous qualitative screening using high-resolution libraries in just one set of experiments. Those suspect compounds which are rarely detected or for which standards are expensive or unavailable are possible to be qualitatively screened without relying on a calibration curve, while common targets can be calibrated against in a single set of acquisitions on the 7250 GC Q-TOF. Changing topics, we'll now discuss powerful exploration capabilities for identification and elucidation enabled by breakthrough technology. One of the most challenging tasks for an analytical lab is the identification of unknowns, particularly in complex sample matrices. One such example is hydrocarbon analysis. We performed this application on the 7250 GC Q-TOF to evaluate its performance in this challenging area. Injection of a gas oil sample yielded a typical hydrocarbon chromatogram, as is shown in the upper right-hand corner of the slide. A time segment from this chromatogram was extracted to generate the spectrum shown in the upper left-hand corner of the slide. Library search provided a tentative identification of 3,4-dimethyl benzothiophene, which its NIST library spectra is shown below the chromatogram. Although the measured and library spectra are similar here, there are some obvious visual differences. There is more low mass fragmentation in the acquired spectra, and it's not quite clear which of the two molecular ion candidates may belong to the compound. While we may have some confidence that this identification has been made successfully, we might like to see more selectivity in our detection. It would be very beneficial if we could produce a cleaner system with less low mass fragmentation and a tilt towards the molecular ion, with a relative increase in the candidate molecular ion to better identify the compound. Ideally, we would see almost no fragmentation, with only a clear molecular ion candidate rising above the baseline. To increase our confidence in compound identification, we would like the ability to preserve or confirm the molecular ion, and also to reduce background signal to produce a cleaner spectrum for evaluation. On the 7250 GC Q-TOF, we were able to generate both of these spectra by lowering the ion source energy, first to 15 eV, then to 10 eV. How is this possible? Through a proprietary low-energy EI source available only on the 7250 GC Q-TOF, and it's available as standard equipment. There's nothing that prevents a conventional EI source from operating a low electron energy to perform softer ionization and generate a tilt toward the molecular ion. Although typically this results in sensitivity levels that are just not usable, or the filaments used burn out extremely quickly as we have to increase the electron current to increase the number of low energy electrons. We've overcome these challenges with a novel source design based on the high efficiency source found in the Agilent GC MSD and GC tandem quad models. The source has been optimized for performance at low energy EI, but still exceeds a conventional 70 eV EI. Optimizations include a stronger axial magnet, modified lens geometry, and a centered filament design. All of these changes allow the source to become even more efficient at ionization, which allows us to trade some efficiency for softness and a tilt toward the molecular ion. Although there may be some loss of total ion current at lower electron energy values, the efficiency of ionization is still high enough to provide usable levels of sensitivity. Additionally, generated spectra are cleaner, yielding better sensitivity and greater confidence. An example of low energy EI for identification goes back to the previously mentioned metabolomics experiment, but it also applies universally across sample types, including food and environmental samples. In the case shown here, a tentative identification of the metabolite kynurenine was made in a mouse lung extract. While the measured and library spectra are quite similar, the spectrum was not deconvoluted, so there are some differences. By lowering the electron energy to 17 eV, there is a simplification of the spectrum with a tilt toward the molecular ion. For this example, the candidate molecular ion experiences not only a relative increase in abundance, but an absolute increase as well. At 12 eV, the candidate molecular ion becomes the base ion. Since there is an abundance increase of the candidate molecular ion abundance at 17 eV, we can use this as a precursor for downstream MSMS experiments. Because the 7250 GC Q-TOF is an MSMS-capable instrument, it can generate product ion spectra. Once a precursor has been isolated and fragmented, the product ion spectrum can be opened in Agilent's Molecular Structure Correlator (MSC) software for analysis. The product ion spectra are evaluated not only for mass information, but fragment information as well. Molecular Structure Correlator uses online services like PubChem and ChemSpider to pull down candidate formula and structures for masses in the product ion spectra with associated likelihoods, providing the analyst insight into not only chemical formula, but compound structure as well. The previous example highlighted a case where a proposed ID was made by library match, and it was compared with low energy EI and MSMS for an independent degree of compound identification. But what happens when a library search returns a poor match or no match at all? In this case, the sample contains a true unknown, and the analytical capabilities of the system must be used to provide guidance on the identity of the compound. This data shows a chromatogram and spectrum from an unknown compound detected in an extractables and leachables experiment that was evaluated on the 7250 GC Q-TOF, where the unknown compound was detected at retention index 1711 with no library match returned. To investigate the compound, the sample was additionally acquired at 10 eV. This resulted in a clean spectrum with less low mass fragmentation and a tilt toward the high mass region. From this data, 2 candidate molecular ions were identified. With each of the candidate ions identified, MS experiments were scheduled to isolate each precursor to generate product ion spectra. Candidate 1 was the precursor at mass 191, while candidate 2 was the precursor at mass 220. With the product ion spectra now available, each of the characteristic masses in the original MS-only spectra were compared to the product ion spectra. In doing so, it becomes clear that candidate 2 contains much of the characteristic ions, and in approximately the same proportion as the MS-only spectra. If we consider the relative similarity of the MS-only spectra and the MSMS product ion spectra of our 220 M/Z precursor, we have some confidence that we've selected the correct precursor ion. Comparing the mass accuracy with the candidate formula, we have additional confidence in the identification. And looking at the isotopic pattern, we have additional independent confidence in the chemical formula determination. With the product ion spectrum from the candidate molecular ion, the molecular structure correlator can be used to propose candidate fragment structures and likelihoods, leading the analyst to narrow the list of possibilities. In this extractables and leachables experiment, the candidate unknown is a benzene methanol derivative, which can be further confirmed by comparison with a purified reference standard, if available. We've gone through the case of not having a library hit to propose a compound identity. However, the majority of non-target screening cases will return a library hit. It is up to the analyst to determine the validity of the match. In this area, the GC-MSD used with deconvolution and library searching is a very practical choice. The GC-MSD presents a great value for both qualitative and quantitative work. There's a reason we sell so many GC-MSDs and have done so for decades. And yet, there are cases where even the venerable GC-MSD needs a little support. Let's go through one such example, covering an untargeted screening of broccoli. After data acquisition and deconvolution, the component list is evaluated. Our first example is a component that elutes at right around 5.6 minutes. The high-resolution accurate mass spectrum closely matches the NIST spectrum for the compound 2,6-dimethylnaphthalene with a score of 94.7. With a GC-MSD, this is where our analysis would end. With the GC Q-TOF, we can perform low-energy EI to gain further confidence that the proposed molecular ion at 156 M/Z is likely the correct choice, and the accurate mass measurement corresponds to a 0.3 ppm mass error with the proposed compound formula. 2 additional degrees of confidence that the identification is correct. But this still provides the same answer as the GC-MSD. A little further down the component list, a library match of 137-trichloronaphthalein is made with a score of 87.2. Not quite as compelling as the previous example, but still quite good, with visually similar spectra between the GC-Q-TOF and NIST. Again, low energy EI confirms that we likely have the correct molecular ion identified. When comparing the accurate mass measurement of this molecular ion to the library compound formula, we find a problem though. A mass error of over 100 ppm. Immediately, the library search is put in doubt. We now need a way to determine what this compound likely is, exactly the task for what the 7250 GC-Q-TOF was built. We'll need to dig deeper into our example to figure out just what this compound is. After confirming the candidate molecular ion with low energy EI, a product ion spectrum is generated. The fragment masses in the product ion spectrum match those in the MS-only spectrum, providing further confidence that the molecular ion selection is correct. With this product ion spectrum, the molecular structure correlator tool can then be used to propose likely structures for the molecular ion and fragments. With this approach, the compound 2,4,5-trichloroisophthalonitrile is exposed. Importantly, this compound is not in NIST, which is why the GC-MSD would not have picked this up in the library search. But this is reported as a pesticide degradation product. Although commercial libraries are extremely useful, the added features of accurate mass data, low energy EI, and full spectrum MSMS capability make the 7250 GC-Q-TOF the qualified choice for investigation and tentative identification of unknown compounds. We've now seen that the venerable GC-MSD is an excellent screening tool, but the limitation of unit mass spectra leave room for doubt. For complete confidence in unknowns identification, the 7250 GC-Q-TOF is a platform of choice by those who know GC-MS. The analytical capabilities of the 7250 GC-Q-TOF solution provides answers where only more questions were previously raised. In this presentation, we've shown quite a few examples of data, but data itself is of limited value without the necessary tools to generate meaningful results. In applications like screening, mass hunter data analysis tools in both qualitative and quantitative analysis allow for seamless, integrated screening against nominal and high-resolution spectral libraries and reference standards in one set of experiments. For profiling experiments, Mass Hunter Profinder and unknowns analysis allow for high-throughput compound detection, which drives multivariate statistical studies in Mass Hunter Profile Professional for different analysis, with optional workflows for compound identification and/or biologic pathway contextualization. Investigation of unknowns is enabled through Mass Hunter Qualitative Analysis, Profinder, and unknowns analysis, with deeper insight possible through MSMS data in molecular structure correlator software. For compound class prediction, statistically trained models can be generated through Mass Profiler Professional to offer predictive insight on future sample sets. The whole suite of Mass Hunter data analysis applications enables users of Agilent MS instrumentation to make sense of the information-rich data generated by platforms across the LC-MS and GC-MS domain. A common set of software tools enables analytical chemists to maximize their productivity across the Agilent MS portfolio. That brings us to the end of our presentation. As we've shown, the performance characteristics of the all-new 7250 GC-Q-TOF promise to move GC-MS analysis forward across identification, quantification, and exploration workflows empowered by comprehensive software tools. Designed with feedback from the user community and optimized for real-world samples and applications, the 7250 GC-Q-TOF strives to equip analytical labs with the tools necessary to solve challenging GC-MS analysis today and into the future. Thank you all for your time and attention. This concludes the presentation.
Thank you, Paul, for that outstanding presentation. And we will now move to the Q&A live portion of our presentation. As a reminder, please submit your questions via the Q&A box. Paul, it looks like we already have quite a few questions coming in from our audience members. Our first question, how would all-ion workflow work for Agilent's GC Q-TOF platforms? And what is the downstream data processing like?
Sure, that's a great question. Thanks, Susie. For those not familiar with the all-ions workflow, as used on the LC quadrupole time of flight instruments, it's a full scan workflow where precursors are then identified for targeted MS/MS experiments. On the GC Q-TOF, and was mentioned in my presentation, we utilize the low energy EI source to do this. Of course, we can schedule targeted MS/MS methods with the GC Q-TOF as well, and then brought into Mass Hunter data analysis software in order to identify those targeted precursors. But again, reiterating what was mentioned in the presentation, by using the source to identify precursors for a targeted method, we can optimize the sensitivity and the power of a library in order to identify precursors, perform targeted experiments, and to ultimately find the compound IDs that we would like with that workflow.
Thank you so much. And can data collected on the 7250 be matched with unit mass libraries?
Yes, of course it can. So mentioned also was the Shore mass deconvolution, and with the deconvolution, with the accurate mass data, we can then utilize the unit mass library, not just an accurate mass library. This is another such example where we can do so to leverage that data for a more versatile analysis.
Thank you very much. We have time for one more question. It is mentioned that low energy EL source is standard equipment. Are other sources offered for the 7250?
Sure, yes. As I had mentioned, the low energy EI source is a combined source, so it can run low energy EI and standard EI. But we do also offer a chemical ionization source. It is capable of both positive and negative chemical ionization and utilizes methane as the carrier gas there. So we do have the versatility of multiple sources for use on the instrument. And this is something that was offered shortly after release of the instrument, but is available now as an option.
Paul, I want to thank you for your presentation today and also for your important research. And I also want to thank the audience members for their outstanding questions. Any questions that were submitted and not answered today by our speaker will be answered via your email address. And the presentation will be available for on-demand viewing through September 2021. Please share that with a colleague who may be interested in today's topic. Thank you again for your participation, and I hope you will join me for our next presentation, Vincent Boulogne. If you are not moving into the new virtual studio, take care, be safe. Until next time, bye-bye. Thanks again, Paul.
Thank you.